In order to scale a decentralized network, you eventually have to stop executing every single transaction on every node. In Ethereum's Layer 1 architecture, consensus dictates that every single participating node must independently replay and verify the exact same computational steps for a given transaction. This strict requirement of global, redundant computation places a hard mathematical ceiling on network throughput and causes the total size of the blockchain state to bloat continuously over time. When network demand surges, users are forced to bid for this highly constrained block space, driving up transaction gas costs exponentially. Optimizing the Ethereum virtual machine, or EVM, offers only marginal improvements. The EVM is Ethereum's primary computation engine where smart contracts run. No matter how efficient it becomes, the baseline requirement of redundant execution across thousands of nodes remains the ultimate bottleneck. True scaling requires extracting the computation process entirely from the consensus layer. Layer 2 zero-knowledge rollups achieve this by decoupling transaction execution from network verification. An off-chain entity called a sequencer takes thousands of raw transactions and processes the smart contract logic entirely outside of the main Ethereum network. To prove this off-chain work was done correctly, the rollup relies on a cryptographic property known as succinctness. Succinctness dictates that the size of a cryptographic proof is extremely small compared to the vast amount of computation it represents. Using proof systems like ZK-Snarks or ZK-Starks, the sequencer mathematically compresses megabytes of arbitrary state transitions down to a file as small as 192 bytes. ZK-Snarks stands for Zero Knowledge Succinct Non-Interactive Argument of Knowledge, a proof system that requires no interaction between the prover and verifier. The main Layer 1 network receives this succinct proof and runs a mathematical verification through a smart contract, bypassing the need to actually execute the underlying transaction logic. If the math is correct, the main blockchain securely updates its state root to reflect the new balances based entirely on the proof. This creates a severe computational asymmetry. Generating the zero-knowledge proof requires immense processing power off-chain, but verifying that proof on Layer 1 takes fractions of a second. Bringing this architecture to general-purpose smart contracts introduces a major engineering friction point. The EVM was built for standard computation, not for cryptographic proving. Previously, developers had to manually write bespoke cryptographic circuits tailored to specific EVM opcodes. An opcode is a basic machine-level instruction that the EVM executes. Translating arbitrary smart contract logic into these rigid mathematical constraints is an incredibly complex and error-prone process. It forces developers to possess deep applied cryptography knowledge, drastically slowing down software development. For the Web3 ecosystem to scale, these general-purpose contracts require a standardized compilation bridge that can generate proofs automatically. Without a dedicated software abstraction layer, zero-knowledge execution simply remains a boutique solution locked behind extreme technical barriers. Zero-knowledge virtual machines, or ZK-VMs, like RISC Zero and SP1, provide this exact abstraction layer. A ZK-VM is a virtual machine designed to output an efficiently verifiable proof for any arbitrary program it runs. In the ZK-VM pipeline, developers write their smart contracts in familiar, standard programming languages like Rust or C++.
The ZK-VM compiles this high-level code into bytecode for a generalized instruction set architecture, such as RISC-V. RISC-V is an open standard architecture used to define how software communicates with a processor. The core operational mechanism that makes this work is called arithmetization. Arithmetization automatically translates the entire execution trace of the program into a highly specific constraint system made up of polynomial equations. This system functions as a programmable circuit. It grants developers EVM-level flexibility without forcing them to directly manipulate the underlying cryptography. A back-end proving system, such as Groth16 or Plonk, then takes these exact polynomials and generates the final, verifiable certificate of execution. ZK-VMs solve the software bottleneck, but they push all the friction onto the back-end. Generating proofs from these massive polynomial constraint systems requires extreme, brute force computational overhead.
The sheer volume of polynomial constraints generated by a ZK-VM creates a severe physical bottleneck in the hardware proving backend. Two specific mathematical operations are responsible for overwhelming standard processors: multiscalar multiplications, or MSMs, and number theoretic transforms, or NTTs. MSMs demand intense parallel processing capabilities and massive memory arrays to multiply large vectors of elements. Conversely, NTTs do not rely on parallel execution. Instead, they require constant, chaotic data shuffling and rerouting throughout the algorithm. The physical breaking point occurs when the datasets for these NTTs exceed the on-chip memory limit, often around 16 gigabytes. When this happens, the data must be transferred over the external network or hardware bus, introducing massive communication latency. This specific data shuffling bandwidth issue effectively throttles the entire proof generation pipeline. Traditional CPU architectures are inherently unequipped to handle this continuous, specialized cryptographic heavy lifting. The first major hardware pivot involves migrating from standard CPUs to graphics processing units, or GPUs, to tackle the heavy parallel processing demands of MSMs. While GPUs feature fast development frameworks like CUDA, they are highly power-hungry and still struggle to resolve the data shuffling latency of NTTs. Field Programmable Gate Arrays, or FPGAs, represent the next architectural evolution designed to directly address the NTT bottleneck. FPGAs provide a programmable hardware fabric, allowing engineers to wire complex cryptographic logic directly into the circuitry itself. This direct integration solves the NTT problem by maintaining high-bandwidth data streams on-chip, completely eliminating the communication delays between the CPU and the GPU. FPGAs offer reprogrammable flexibility, but the ultimate endgame for zero-knowledge hardware lies in application-specific integrated circuits, or ASICs, and verifiable processing units. ASICs permanently etch the exact logic for MSMs and NTTs directly into raw silicon. The severe trade-off is that ASICs possess write-once business logic. Any protocol updates require a complete rebuild of the system, forcing a new 12 to 18-month design and deployment cycle. Despite this extreme inflexibility, ASICs deliver the maximum theoretical throughput required to support real-time, high-volume decentralized finance. Scaling Ethereum is no longer constrained by the limitations of decentralized consensus software. Through the integration of rollups and ZK-VMs, it has evolved into a pure computer science and silicon engineering arms race.